Construction journey, and this time we're going to look at similar figures as well as similar triangles. When we're showing similarity, we just use the little inye symbol and we don't use the equal sign for congruence. But if two triangles are similar, their scale factors are going to be the same. So when you divide the corresponding legs, you should get the same ratio. So that's going to be what we determine as our scale factor. Two polygons that have the same number of vertices, and again, that's kind of saying the same number of sides by default, are similar if we have a one-to-one correspondence between the vertices of one and the other, and that the corresponding interior angles are congruent. So kind of like the angle-angle congruence, or angle-angle similarity theorem for triangles, and congruent sides are proportional. So the takeaway for this is two polygons are similar if they have corresponding sides that are proportional, meaning the ratio is the same, and congruent angles. We need both of those to happen. Triangles can be similar by side, side, side. They don't have to just be congruent with that one. If the ratios, when I divide the corresponding sides, are the same for all three sides, then they're going to be considered similar. If I have two sides with the same ratio and a congruent angle between them, I can also use side angle side similarity for triangles. And then last, like I mentioned before, if I have two angles that are congruent between two triangles, I immediately know they are similar. And obviously by default, if two angles are congruent, so is the third one, but we just call it angle-angle similarity. So if I want to look at this figure, a lot of students really struggle with seeing a trapezoid and then a triangle. So that's kind of a challenge to work on with your students. And I use different colors when I'm teaching this to show the different parts of the triangle. So I want them to see that there's one big triangle from A to C to E. So that's a big one. And then we have B, C, D. We don't want them to see that trapezoid there. And because I know that AE is going to be parallel to BD, that means that I'm going to have congruent corresponding angles that are going to be formed. So that means that CBD is going to be equal to CAE. And then CDB is going to be congruent to CEA. So I have two congruent angles, which means I can say these are similar by angle-angle similarity. Here, I'm looking at these two triangles and I'm told that BD intersects AE. So that means that I have this intersection point right here. I have a right angle. I know that angle B and D are equal because they're right triangles. And I also know that this angle C is a vertical angle. So these are congruent in and of themselves, which means I have congruence by angle-angle similarity. In this figure, if I'm looking to solve for the value of x and I'm told right here that these two triangles are similar, I'm going to set up that proportion and I'm going to fill in the values of the proportion. Well, I know that AB is 5, ED is 8, so 5 over 8. Then I know that CD is just going to be x at the bottom and BC is 12 minus x. One of the biggest things that we see here is that students don't look at the actual information the same way where it's 12 minus x. So that could be part of the issue there. If I'm looking at properties of proportions, if a line is parallel to one side of a triangle that's going to intersect another side, and it's going to divide those sides into proportional segments. So I'm going to have proportional again, meaning that ratio there. If parallel lines are kind of cut off, so they're cutting this triangle in pieces, then they're going to cut off congruent segments on any transversal. So all those little segments are going to be congruent. And then lastly, one of our last steps in this slide would be using a compass and straight edge to divide a segment into those congruent parts, kind of like we just did in that triangle. So these would be the construction steps. And the real skill that we're teaching here is that the measurement on the compass is the same, even though those points aren't on a vertical or horizontal line. So they may not look congruent, but they truly are congruent. The mid segment of a triangle is something a lot of students have trouble naming, so we want to work on using the appropriate term there. We know that we have congruent sides on either side of there, and we know that the third side of the triangle is going to be, that little third side is going to be half as long. So if a line bisects one side of a triangle and is parallel, so here we have it parallel MN to AC, it's going to bisect the third side and therefore be a midsegment. So when it bisects, that's what's creating this right here. If I'm looking at a quadrilateral and I want to find the midpoints of the sides and I want to know what kind of quadrilateral is this, I can start breaking it down by looking at NP. It's a midsegment in that triangle BCD. And since it's a midsegment, that's telling me that this is congruent to this and this is congruent to that. So that I know that NP is going to be parallel to BD. Then I'm going to know that MQ is the midsegment there, so I know they're going to be parallel. Therefore, MQ has to be parallel to NP. And remember, that's going to tell us something about the shape. So we can also show through that same process but different points that MN is parallel to QP. Since I have two pairs of parallel sides, it's going to be a parallelogram from our properties earlier. The centroid of a triangle alludes to the median, and the median of a triangle is a segment that's going to connect the vertex of the triangle to the midpoint of the opposite side. A triangle is going to have three medians. The three medians are concurrent, and the point of intersection G is going to be the center of gravity or the centroid of the triangle. Again, we just kind of want to start talking about centroid. We want to use vocabulary with these students. We don't expect them to construct a centroid, but we kind of want to know that's the center of gravity. So if we're trying to put something on a table and balance it, we're really looking at if that point that's at center of gravity is really centered. The centroid of a triangle divides each median into a ratio of 1 to 2. If I have some indirect measurements, similar triangles have been used a lot to make those indirect measurements on larger objects. So we can actually find the height of a pyramid using similar triangles. And if you look at the two blue triangles, they are going to correspond to one another. And so here's an example. If I have a sunny day and a tree is casting a 40-meter shadow, and I have at the same time that I'm holding a meter stick, how tall is the tree? Well, I'm going to set up my ratios of x to its corresponding side, and the other triangle of 1, notice how those are in the numerator, and 40 to its corresponding side in the other triangle of 2.5. Then I'm going to cross multiply and divide both sides by 2.5, and I'm going to get 16. So that's how we're going to solve similar triangle problems, and the goal is that we can eventually solve these types of word problems.